Welcome to LIB Academy. Let's talk about operators and observables in quantum mechanics. This is our second video in the playlist Quantum Mechanics. What is an observable? An observable is a property of a system that can be measured. Property of a system and a state that can be measured. Examples of those properties are momentum, energy, which could be kinetic energy or potential energy, right? Those are observable. Spin is also part. Spin is an observable, the property of a system that can be measured. Position is also an observable. Generally, anything that is quantifiable in quantum mechanics is called an observable. The next thing we want to look at is operators. What is an operator? In mathematics, an operator is anything that is telling you to do something, right? For example, the plus sign, the addition sign is an operator. The multiplication sign is an operator. Subtraction, square root, all of these are operators in mathematics. Take second derivative. Take second derivative with respect to x. All of these are operators. So in quantum mechanics, we have operators in quantum mechanics that we need to know them for our journey in quantum mechanics. This video is a step-by-step video to help you in your journey, throughout quantum mechanics. So we'll try to keep some of the things as they are and tackle them in the subsequent video. So in quantum mechanics, we have operators like P cap, which is momentum operator. Momentum. We also have the H cap, which is the Hamiltonian operator. Hamiltonian operator. This represents the total energy of a system. We'll talk about it later. And we also have the X cap, which is the position operator. This is also an operator in quantum mechanics. But we will be talking much about this, things like this in our subsequent videos. So all you need to know in this video is operators and an observable. An observable is basically the physical property of a system that you can measure: momentum, energy, spin, position. An operator is something that is telling you to do something, telling you to operate, right? In mathematics, we have the addition, the root sign, the derivative sign, and these are examples of operators in quantum mechanics too. So now, one will ask, why do we need different operators in quantum mechanics? Why do we need an operator for momentum, operator for Hamiltonian, the total energy of a system, position? Why do we need them? We need them because we are trying to understand things like how we were able to understand things we want to understand things in the quantum level, like how we were able to understand them in classical physics, right? So in classical physics, we assume that the physical quantities, which is the observables, can be measured. They have definite values. Let's say in classical physics, we assume that position, velocity, and momentum are finite. They are definite, right? So we can measure them directly. Well, that tends not to be the case in quantum physics. Quantum physics or quantum mechanics is the same thing. For example, in the classical world, if you throw a football, if you throw a ball, you can directly measure where the ball is, how fast it's moving with the help of Newton's laws, and the path the ball has taken. That is in the classical world. You can measure these things directly with the provided formulas, right? You can measure velocity, position directly. But in quantum physics, things are different. So we need to introduce another language before we can be able to work with quantum systems or predict the behavior of a quantum system. Because a particle like in quantum physics, a particle like electron is not described directly by position or momentum first. Instead, it is described by a wave function, let's say psi, a wave function psi. And this wave function is not itself an observable. You cannot directly see or measure this wave function, right? What we actually observe comes from mathematical operation on this wave function, right? For instance, let me just write a certain equation for your understanding. Let's say we can say an operator A will operate on our wave function to give us energy and then our wave function again. So you could see that this wave function is giving us, something about the electron. And when we operate a certain operator on the wave function, we are going to get energy and a wave function again. So you see that we were not able to measure the energy directly, right? But we did some operations before we got the value for the energy, right? We'll be talking about equations like this in the later videos. So what I want you to understand is that we need to introduce another language, operators, which are quantum operators. Another example is you can take into consideration is that, let's say this wave function is giving us, telling us the behavior of the electron. The probability of finding an electron, we can work on this wave function to get the probability of finding an electron, which is basically this squared. So you see, this wave function directly was not the observable, but it is giving us information to work on to get the observable, right? So that is what I want you to know. So in classical physics, we work directly with the position, with the observable position, velocity. But in quantum physics or mechanics, we first work with the wave function, then extract observable quantities from it using operators and probabilities. So that is it for this video. See you in the next video. Thank you for watching, and don't forget to like or subscribe to the channel. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.